Recording in progress. Okay, so this is the second day of our Eicefala, and one other field of science that we are having in this meeting is it would be a neuroscientific part of the meeting where we try to relate behavior and perception phenomena with the neurophysiological phenomena. In that context, we invited Professor Rafael Laboissière to present the results he obtained with Adelaide Santana and partially with me too, about neurophysiological correlates of phonemic categorization. Rafael has been a colleague for decades now, maybe half a century in the near future. And we expect you to enjoy his presentation. We will have some time for questions at the end. So Rafael, the audience is yours.
Okay, thanks, Hani. Could you just tell me how much time do I have for a presentation?
45 minutes.
Okay, good.
So that we have time for discussion. If you do 50 minutes, yesterday we had an interesting discussion. So if we leave 15 minutes for discussions, it will be okay. If you need 50 minutes, it's okay, because one of the talks in the afternoon was canceled. So one of the short talks, but 45 to 50 minutes.
Okay, perfect. So first of all, thank you very much for inviting me for this Eicefala. So I have been in Eicefala since the beginning, I think, yeah, of this meeting series, and I'm very pleased to be here again. Unfortunately, we are offline, so sorry, we are online. We are not in presence, but I hope that the next one will be done again in Brazil. Yeah. So I will present to you some neurophysiological correlates of phonemic categorization. So my talk is really not about the study that you did, but I'll do a review on the neurophysiology of speech production perception. I talk about cerebral models of speech processing. I talk about categorical perception and examples of neurophysiological studies on phonemic categorization. And then I just do some considerations on the methodology. So both or in the techniques that you can use for acquiring data, for processing data, or for doing the behavior studies. Yeah. And just some advertisement here. So this talk is just a review of the literature on the subject. If you want to know more results about the recent empirical study, the study that Hani mentioned, so come back on Thursday. And then there's a talk called entitled Behavioral and Neurophysiological Representation of Speech Phonemic Units that will be given by Adrielle. And then this study was done in collaboration with Hani and Adriano. So I'm not going to talk specific about this study in my talk. So the first part is just neurophysiology of speech production perception. So let's talk about a little bit of story of the history, of the speech production and perception in the neurophysiology domain or in neuropsychology. So you probably all know Paul Broca was a French scientist or neurophysiologist who lived in the 19th century. And he came across a patient that's called Monsieur Le Borgne in the literature, or Monsieur Tan Le Borgne. Tan is the nickname of this person. He was a young man who came to the hospital where Broca worked, and he has a very, very strange pathology. So he was totally normal, has no problem, mental problem or behavioral problem, but could not produce speech. And this condition was a progressive condition. So he had a progressive loss of speech since 21 years before he came. So he came to Broca around 1861. And then, so Broca examined this patient, and then he died several days later because he had a uncontrolled infection, so a generalized infection, not related to the problem itself. But he was hospitalized. And then Broca described this aphasia as expressive aphasia. So he could understand everything, but cannot produce. And he could only produce a single syllable, was tan. So he spoke like this, tan, 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 with the write prosody, you could imagine that this is speech, but it could not express himself. He wanted to express. Apparently, he could if he had not had this pathology. And so when they did the autopsy of the brain, they saw a lesion here. It was a lesion caused by AVC or a stroke, okay, in this region, and it was a very specific region here. Let's look at a more modern brain. So just for you to be reassured, the brain didn't change from the 19th century to the 20th century. It's the same brain, but this is it's only a more modern representation of the brain, a picture of the brain. And because this here is a drawing in a book that was done. So just to make things clear here, because I will talk about this later in the talk, you all know that the brain is, so this, what is called the neocortex is this part of the brain here. Here is the cerebellum that's there. And in this cortex, it's very specific to the humans that you have a very convoluted cortex here. So you can put a bigger surface in the smaller volume of the skull. And this cortex is composed of gyros, or gyri is the plural of gyros, or sulci is the plural of sulcus. So gyros and sulcus here. Sulcus are the convolutions here, and the gyros are the things that come out of the cortex here. And we can divide the brain in lobes, like the occipital lobe, where have the vision function here. You have the temporal lobe, we have the auditory function here. You have the parietal lobe that's separated from the frontal lobe by the central sulcus here that you see. So in the parietal lobe, we have the somatosensory cortex, that is this part here, and the frontal lobe, we have the motor cortex here. This is typically where you see the homunculus in the brain when you look at this. So this area here that was found in the autopsy of Monsieur de Borgne is what we call now the area 45, or the Broca's area. And this number comes from a classification that was done by a German scientist, Corbinian Brodmann. And this is the reason we call this the Brodmann area number. Yeah. So this 45 is the area for the Broca areas here, where the Le Borgne had the lesion. And then people thought at that time, at the end of the 19th century, that speech is related to this region here. This is the speech region. And if something comes to speech, it's here. But then other neuroscientists, so like Carl Wernicke is very, very famous neurophysiologist, was born in the 19th century and died in the beginning of the 20th century. Is a little bit younger than Paul Broca. He studied very extensively the aphasia in the patients. And then he found another kind of aphasia that is today called the Wernicke's aphasia, is what we call the receptive aphasia, in contrast with the expressive aphasia of the Broca's, in the Broca's area. And in this aphasia is very different. So people can really talk fluently with all the phonemes, all the prosody, all the sentence, but the speech is disordered. Doesn't make really sense what the people are saying, but they can produce speech. So, and they have a problem to understand the speech, which is contrary to Broca's patient, so Monsieur de Borgne, who could understand perfectly but could not pronounce. But some people who have receptive aphasia cannot understand but can produce speech. And they have also problems in silent reading. And this aphasia is associated with the area 22, the Brodmann's area 22, that is in the parietal lobe. And this is today is called the Wernicke's area. So you have an area that's more specialized in speech understanding, and the other more specialized in speech production. But it's not all the story, because you don't have only these areas I showed to you in a minute, but we have also to study what happens in the connectivity between the areas in the brain. So this is a paper that appeared in 2015. It was done by Michel Thibault de Choten and his team when he was in Paris. He's a colleague of mine as a French CNRS researcher too. He's now in Bordeaux, but he did this study when he was in Paris. What he did was very interesting. He took the brains of these three cases here. So in the middle, we have the Louis Victor Le Borgne. This is the Broca's patient. The brain is conserved until now, up to date. And they took the brains of two very famous men who had also have lesions, and these lesions were associated with very specific deficits. So this is Phineas Gage. It's an American railroad constructor fireman, and he lived in the 19th century too. And he had an accident when he was working, and this iron rod here entered his face, the eye here, and crossed the skull in the frontal region. And then he lost part of the frontal region. And Henri Molaison, he's more recent. He lived in the 20th century and died in 2008, if I remember correctly. And he had another problem. He was an epileptic patient, have so epilepsy crisis, and then he got the part of the temporal lobe removed, so where you have the hippocampus. So he had memory problems. And Phineas Gage was totally normal, could speak, could do everything. So he lost an eye, so he was blind of an eye, but otherwise he could do everything. But he had behavioral and personality problems. He was another person after the accident. So he died quite young at 47 years. Anyway, but these three cases were they are seminal in neurophysiology, because these people, you could associate some deficits in behavior or in function to the regions of the brain. So Phineas Gage had this frontal area here removed or damaged. So the Leborgne had the lesion in the Broca's area, and Molaison have a part of the temporal lobe removed. But what they did, they took the brains of these three people here who were conserved, and they did what they call the tractography. So they looked at how damage was the tractography, so the tracts of or the nerves connecting one area from the others. These are the name of the tracts here in the brain. And they concluded that there was, besides the region that were damaged, there was disruption in the connections, projection to the areas distant from the lesion. So the fact that you have a lesion here can induce other problems in the regions that we are connected here. Yeah. So this means that the damaged tracts link to the areas that are considered functionally engaged in the tasks that are related to emotional decision making in the case of the Gage, in the language production in the case of Leborgne, or in the declarative memory in the case of Molaison. I didn't describe it, but Molaison has had a very, very strange pathology that he could not form new memories. It's like you are just start again the same day every time. This was his problem. And so based on that, so I talked about other cases here, but let's come back to the speech processing. People had tried to do cerebral models, so I'm not going to show you all the models that exist, but this is a very, very influential one done by Gregory Hickok in a paper in 2014. So what he says is that we have the vocal tract where you produce speech. Of course, you have to articulate the articulates of the vocal tract here under control of a motor phonological system, as he called. And this speech goes into the ear and then goes to the auditory phonological system, this where you can do the sensory targets and the prediction of what you hear or what you produce. And then there is some internal model here where you do this auditory motor translation between the auditory part and the motor part here. And everything is linked to a lexicoconceptual system. In the same, so and then you can have the predict pathway here that is in green, and you can have the correct pathway here that is in blue. Anyway, this is a very, very broad model. And then in the same paper here, they go into details of this model. It's the same thing as before, but more detailed, where he separates the word or lemma level and the conceptual system here. And he separates the two parts here, one that is really dedicated to the articulatory feature or the articulatory feature clusters, and the other that is to associate to the syllables here. And then you have the same scheme here of communication between these areas for the syllables or for the articulatory level that is more close to what you could call the phoneme. because he calls this the motor phoneme programs here, that is essentially in M1 is the primary motor area, and the somatophoneme targets that are in the S1 area here. And then you have this coordinate transformation here that goes through the cerebellum. And at a syllable level here, we have another organization here where we have the auditory syllable targets that are in the superior temporal gyrus and the superior temporal sulcus. Remember what I just showed to you about gyrus and sulcus. And here the monosyllable programs that is in the Broca areas. So sometimes Broca areas appears as the Brodmann area 44 or 45. Yeah? I think that both are considered as the Broca area. And you have again this coordinate transformation here that's done in SPT. Just to make clear what they mean by this model, or in terms of the physiology. So this is based on a thing that Gregory Hickok did with David Puppel in 2007. This is a very seminal paper too, in 2007, that appears in Nature Review of Neuroscience. And this is essentially the same thing that you saw before, but it's more detailed in terms of physiology. What you have here is that in the temporal region here, you should have some processing, so some phonological processing here. Okay, this is done by in the primary area, auditory primary area here in the superior temporal gyrus here, that is in green, sorry. And this has connections with a phonological network that's in the mid of the superior temporal sulcus here, in the mid of the temporal lobe. This is the yellow part here, okay? And then after this processing here is done, and then things separate into two streams. This is what you call in neurophysiology the dorsal stream, dorsal because it goes to the dorsum of the brain that's here, and a ventral stream that goes here, so in the inferior part of the brain. And then you have, after you have this phonological network that is active, and then things separated here in a lexical interface here that is done in the junction between the lower part of the temporal lobe here, okay, both in the middle, posterior middle temporal lobe, this part here, and it's bilateral, okay, but it's has a weak left hemisphere biases. This is totally bilateral, yeah, the green and the red here, and then goes to the anterior part of the temporal lobe. That's the combinatorial network, that as he called here, and at the same time it goes through a dorsal stream here that goes through this junction here. This is what's called the SPT. Is the junction between the temporal and parietal regions here, and this is close to the Wernicke areas, as if you remember what I just told to you. And then goes through the premotor area here. The motor area is here just before the sulcus and the central sulcus, and this is the premotor area, and this is the Broca's area, and this Broca area here is responsible for the articulatory network that you saw in the Broca's study that I just showed to you. And then this process here, of course, there are communication between this combinatorial network here and the articulatory network, as you saw in the previous model. And also you have a very, very widely distributed conceptual network, because when we talk about speech, we talk about phonemes, of course, syllables, but then words, and these words have meaning. And this meaning is really distributed everywhere in the brain. This is what they call the conceptual network here. And one thing in this paper here that is interesting too is that he separates this segment level representation here and this syllable level representations, which have, of course, interactions between them. They separate them when you receive the acoustic input into two streams here, and these streams are related to the frequency bands of the signals of the brain signals, and this is what we call the theta range sampling network here. The theta is a region of frequency in the brain oscillations that is between 4 and 8 hertz. Okay, it's no wonder that this is related to the syllable here, because the syllables is more or less 5 hertz in speech, in average. And then you have a gamma range sampling network, and the gamma range is above 30 hertz. Okay, and this will represent the phonemes here, or the segment level representations in the brain. And all these phonemes and syllables will contribute to the lexico-phonological network that is bilateral. But this here is probably bilateral, but this here is right dominant, this syllable processing thing. And so the question that you ask here is that, okay, this, we can imagine that you have some kind of phonological representation, but can you have a representation of the categorization of phonemes in the brain? That's the third part of my talk that I'm going to present you now. And categorize actually is almost associated to cognition. This is an idea that comes from a philosopher, Stephen Harnett. Yeah. Because actually we categorize lots of things, not only speech. For example, here is a continuum between two faces. These two faces here are the normal faces. Is a person that is angry here, and a person that is showing a disgust. Okay, and what you're seeing here is a morphing between this angry face and this disgust face. So these are not natural things. The person didn't do these expressions here, only these two at the extremes. So they are continually morphed here, okay, from the angry to the disgust. But what you can see, at least me, I can see that all these faces here are angry. This is a little bit ambiguous. Huh? And all these faces here are disgust. So I'm categorizing this face here as a disgust face, and this is angry face, even though it's totally continuous between here and here. I could say here, for example, is 20% angry and 80% angry and 20% disgust, but I never say this. I always categorize. This happens also with colors, for example. If I do a continuum of color here between the red and the yellow, so these colors here have a continuous. So if you take the physical property of this color, which are the frequency of the electromagnetic oscillation, and then you see a continuous change in the frequency here. But then we categorize this. We put boundaries here. So everything here is red, everything here is orange, and everything here is yellow. So a little more dark and light, but it's yellow. Okay. And I will not say that this color here is half yellow and half orange. I say it's yellow. Okay. And for example, this doesn't happen in some cultures because colors is also a cultural concept. For example, the Indians in Brazil, many ethnies in Brazil, they do not distinguish between black and blue. So they could not make the difference between Atlético and Cruzeiro, I think. And because for them, this is the same color actually. And essentially this is what the sky does when it goes from day to night. And for them, there is no boundary here. This is blue, everything, okay? So we can categorize, and this is also related to culture, or in the case of speech, of course, and then you come now. We categorize because you are in a language that have these distinctions. And the way that people started looking at the categorical process of speech was done in the 60s, essentially by this work by Lieberman, when they construct this stimuli here, which are just format transitions. Okay, it's a format transitions where the F2 here goes from a very low value here, around 1020 hertz, 200 hertz, and goes in the middle here where it's almost flat, and then to the end here, the stimuli 14, it's very, very high, so it's above almost 3 kilohertz here. The first format is doing almost the same. This is very synthetic signals, and this here is heard as a ba in this case. Here's heard as a da, and this is heard as a ga. And then what you you have, if you present this stimuli to people, they will categorize them. So they will have some things here in the middle that will be always identified as that. Here always is be, and here always is a get. And someone is in the middle that is a transition here. And this is what you call the identification data. I present one of the stimuli and ask the person what they hear. And we do also pairs of stimuli. So I take the stimuli around 2, so the 1 and 3. I present this to the person. And then I ask if they are different or not. So what happens here is that only those here that are in the middle has a very, very high discrimination score. And those who are here in the region where it's flat here, they cannot distinguish. So I cannot distinguish this. So I have 50% of saying, okay, it's different or not. Okay, because this is a forced choice task. And then people came and said, okay, this happens in the voice for the place of articulation in voiced stops. Okay, and also for the VUT, so between ba and pa, for example. And you have this nice sigmoid curve here for the identification, and for the identification. And for the discrimination, I have this thing here. If I take two stimuli here in this region and 2 stimuli here in the region, I cannot distinguish them, but I can distinguish if I take 2 stimuli here and here. I can say that they are different. This happens for consonants and happens less for vowels, as you can see here. This is the distinction between E and I. Okay, it's and sheep and shit, for example, in English. And this is the reason people say that the vowel is not categorical, vowel perceptions are categorical. This is disputed. I'm not going to enter in this thing. We talk about this later in the talk. Let me just show some examples of neurophysiological studies of phonemic categorization. There are many studies about this in literature. I just summarize 3 of them here for you, yeah? And with different techniques and different methodologies. Yeah? And this is a study done in 1999 by Ackerman and colleagues. And they were interested in studying the cortical VO2 representation. They did this with a MAG technique. MAG is magnetoencephalography. I talk about this later again. And they did a oddball procedure here. What they did is that they presented to the people either the syllable da or ta. Okay, they were listening passively. They didn't have to recognize anything. And so they differ by the VOT. So you have a VOT that's 10 milliseconds in English, because in Portuguese, the da has a negative VOT. And they have a VOT of 10 milliseconds in English, and the ta is aspirated T, has a VOT of 60 milliseconds. And then what they showed here, when they look at the evoked response here, so the stimuli was presented at 0, at time 0 here. And then you have what you see here is the N1 wave that is happens typically between 0 and 100 milliseconds. And then you have the P2 wave here. And these 2 syllables here, even though the N1 is almost the same for da, who is the light curve here, and ta, okay, they differ in the P2 here, okay? So this is not related. Really, the N1 is related to the onset of the stimuli, and the P2 is related to the VOT somehow. And here, this is the measurement by averaging all the electrodes in the left side, which are in the solid lines here, or the right side. This is in the dashed lines here, okay? And then what they showed is this is an oddball technique. So the oddball, you present the da, 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 da very frequently, and then suddenly you have a ta. And then what you measure is the mismatch negativity. That is the curve here, okay? Is the difference between the mean value for the rare da, for example, and the mean value for the frequent da, okay? And then what you see here is that, again, the solid lines is the left hemisphere, and the dotted line is the right hemisphere. This is for the da, and this is for the ta, okay? And what happens, even though the P2 is very different here, these curves here show more or less the same thing for the mismatch negativity. And there's a difference between the rare and frequent, again. And what happens is that this negativity here is increased in the left side of the brain. And this is what makes this author think that really if you have some categorization of data or some phonemic processing of VOT at least, they will be more pronounced in the left hemisphere. This is the conclusion of this study, okay? And let me talk now about another study that was done in 2010 by Chang and colleagues. So Chang is a medical doctor, and he conducts surgery in patients. And then he was interested in how the categorization will happen very, very early in the superior temporal gyrus. And I'll show this in a moment for you. This is stimuli that they use. This is essentially the same as the stimuli that were used by Lieberman that I showed before. This is the ba here. In the middle, you have the da, and here you have the ga sound. Okay, I think that the vowels are here that are pronounced. And they are very short, and they are only 50 milliseconds of the stimuli here. And then this is the result of the behavioral study that they did using this stimuli here from 1 to 14. Okay, and they showed what's classic here. So both the identification task, you see these plateaus for ba, da, and ga, and you see the identification in the discrimination task here. You see that you have this stimuli here that is between the 4 and 6. You can distinguish between the 9 and 11. You can distinguish, but for example, you cannot distinguish between the 7 and 9 that are here in the middle of the da region. Okay. And then what they did is that they did surgery in patients. I don't remember which kind of surgery it was, but they opened the skull and they placed a electrode array here. It's 8 by 8, so you have 65 electrodes here. It's very dense, and they put exactly in the superior temporal gyrus. So the temporal lobe is here, if you remember, and this gyrus here is the superior temporal gyrus. Okay. Is where you are expected to have the acoustic process. So this is the primary acoustic area where the signals converge when they come from the ear. And then what they notice, if they took the energy, the global energy here, okay, in this region, they notice this kind of response here. Looks like the response that you had before for the N1 here, okay? So the energy increases and then decreases here. So the signal come here and does something, and this happens for the ba, for the da, and for the ga stimuli. So the ba is the 1 to 4, da is the 6 to 9, and ga is 10 to 14. And then what they did is that exactly here where you have the peak at 100 milliseconds, they took a picture of the electrodes here, the amplitude of the electrodes here. And then what they saw is that for each one of the stimuli here, okay, they have a different picture here. This is only shown 3 of them here. Of course, they have 14, okay? And then this is a matrix of data, of course, can have different values here. Then what they did later was to take this picture that they took here at this electrodes here. They took this picture here at 0, here at the point 2, that is 100 milliseconds, and then later when the activity goes down, this is the point 3 here. And this is a representation of the confusion matrix between the stimuli that's presented here, from 1 to 13. I don't know why they took the 14 out, but they go from 1 to 13 here. And then this is at the point 2, and this is at the point 3 here. And what they do is that they run a principal component analysis on this data here, and they show that at the beginning we have a very confusing values here for the stimuli from 1 to 13, and then they separate here more. You have a separation in the representation here at the point 2, and then you have a confusion again at the point 3. Okay, this shows that if there is some categorization here, so they are grouping the stimulus 1 to 4 here, 5 to 9 here, and 10 to 13 here. This happens more in the region 2. So this makes this alpha think that you have this very low level and very low latency categorization of the phonemes, okay? And another study that was done more recently in 2013 by Bidelman and colleagues, this is a paper published in Neuroimage. And what they did is to use now, so the first study that I showed used the MAG, so magnetoencephalography. The second one used this electrode placed directly on the cortex. And this study here just does EEG, classical EEG, okay? And in the classical EEG, when you have this is the classical response that you can have on the scalp here. And then you have, when you have a syllable or a vowel that comes here, and then you have a very fast oscillations here that are very early in the signal, and then you have this very low frequency oscillations here. And what this paper tries to do is to separate these two things, saying that there is something here that's above 80 hertz that is very early in terms of signal, and this is related to what they say the brain stem here, so before you get to the cortex. And this very slow oscillations here that is below 30 hertz, they are more cortical processing signals. And what they do here is that they do a continuum between the vowel A and the vowel U. I will come back to this later in my talk, because doing a continuum between A and U is a little bit absurd, but anyway. And then what they have here is that when they look at the representation here, C is a representation of the signal here. You can see the formats that vary here in this brainstem signal. So some kind of continuous representation of the second format here, which would distinguish the A from the U, actually. Sorry, this is the first format between the 600 hertz and going to 400 hertz here. This is F1, sorry. And this F1 here is represented continuously in the brainstem, okay? But when you look at the low frequency signals here, so here we're talking about 200 milliseconds of scale here. And this is where the vowel appears. And then you have again this N1 and P2 complex. So Adriele will talk about this in more detail on Thursday. Yeah? And then what they observed is that you have some grouping here. So the vowels that are in the extreme close to A have a similar response here, and the vowels that are close to U has a similar response here. Okay. I discussed this a little bit later because I'm not convinced that this is really categorization here. But this is what they found, and then they used a very clever procedure. It's close to what Chang used in the previous study that I showed in 2010, by using this dissimilarity between the signals here. This is a matrix of dissimilarity between the stimuli, the response to the stimuli 1 to 5, okay? And they do this in the brainstem, and they conclude that they are essentially dissimilar everywhere. This is what you observe here. This is the result of the discrimination and identification task. And here you have some grouping here. So the two stimuli 1 and 2 group here, and the others group here. This is akin to the identification, the classic identification that you show in the behavioral task, and the discrimination that you show here too. So they separate more here, 1 and 2 versus the 3, 4, and 5. This is essentially what happens here. And this is the model of Bidelman. That's what you have is that you have a continuous representation in the brainstem. So all the characteristics of the signal are continuously translated into neural information. And then at some point you have a cortical transformation that does this sigmoid function here, and then you transform to the vowel, and then this gets this behavior that you call the categorical perception of phonemic categorization. And now this is the paper that you just published now. So this is some advertising for our paper again. And so this is the paper that was published in the BMC Neuroscience by Adriele, Hani, Adrian, and me. As I already did the advertisement, just come back on Thursday. I'm not talking about this paper now. Now, at the end of my talk, I just talk about the methodology here quite quickly. So the methodological aspects of this kind of studies, and I do this in three parts. One will be the data collection part. The other will be the data analysis, and what is the behavior methodology that you can use, and some suggestions for improving this kind of studies. So in terms of neuroimage techniques, you have many techniques. So one technique that is was very used in the last century was the PET technique. It is a positron emission tomography. This was very popular. It's very similar to MRI, but actually it's based on the decay of a substance that we introduce in the subject. So inject the substance, and this is a radioactive substance, and then it will decay somewhere in the brain. And where it decays more, this indicates that you have more activity of the brain at that point. Okay, so this technique has some pros, some advantages. And the advantage is that it's provide an image of brain activities like MRI. It was one of the first ones to be used, actually. And have some disadvantages here. It's very expensive to use. And you have to use a radioactive material that is injected in the subject. This is very invasive now. And then came the functional magnetic resonance imaging, so fMRI, to be short. And has some advantages here is that you have no X-ray and no radioactive material that is used. You have a very good spatial resolution, this technique. It's safe, it's painless, and non-invasive, okay? But has some advantages too. It's very expensive. It's highly expensive, this technique, because you have these magnets that are very expensive, and also needs a very high level of maintenance. And you have a very poor temporal resolution, because this technique here, the fMRI, if you don't know, it's based on what you call the baud signal. The baud is the signal that is responsive to the metabolism of the brain. So indirectly, we look at parts where the metabolism was high, so with lots of oxygen there, or hemoglobin actually, that was conducted by the hemoglobin to the brain. And then this is what gives the signal that you have. But this is a very poor resolution, temporal resolution. So in the orders of a couple of seconds, even 5 seconds. Yeah. And one of the problems too is that you can have no metallic device close to it, because it's very magnetic, actually. So people with pacemakers cannot be tested. The participant must be collaborating. It has to be very still. If it moves 1 millimeter, then things can go wrong. And you cannot use, of course, claustrophobic participants, because they are in a very closed space. Some people so some people fear this kind of experiment. And then you have the ECOG, is electrocorticography, and this is what I showed in the Chang et colleagues 2010 paper. So essentially what to do is you open the skull and you just place a electrode matrix here. In this example here, you have something that's placed close to the sensory, so the somatosensory and the motor area here in the brain. So the advantage is that you have a very good temporal and spatial resolution. This is what Chang did in 2010. And the disadvantage is that it needs surgery, okay? So essentially what they do this is with pathological people. And when they open, they take advantage of the surgery, and then they do the experiment that's not really related to the surgery. It's investigating areas in the brain where so the function is correct, is not damaged, actually. And by the way, people can use this today now, for example, for people who are paralyzed, so cannot move the limbs. You can implant some kind of electrodes like this here. And from what the people are thinking, they can move, for example, a robotic arm. This is something that's very promising, but it's not something that you can do easily in our domain, of course. And another invasive technique that is used is the IEEG, is the intracranial electroencephalography. Essentially, it's the same technique as the electroencephalography, but instead of putting the electrodes on the scalp, they introduce electrodes in the brain. So it's like a shaft here that goes into the brain with several electrodes here. So you can record precisely the activity of the neurons close to those electrodes. Okay, so the advantage is that you have very, very good temporal spatial resolution, but the disadvantage is that it needs surgery, and this is only done today with pathological people, typically people who have epilepsy, and then you have to do a survey to detect the centers which are epileptogenic, so that generate the epileptic seizure that these people have. So this means that you can only use this in pathological patients. You cannot use this today in normal patients, of course. And this is a problem because some pathological patients have all other problems than speech related problems. So this can complicate things here, but it's a technique that's very, very used as well. Okay, and another thing too is that the electrodes, they measure a very, very local activity here of the neurons. So this means that they cannot have a big picture of what is happening in the whole brain, as you can have with EEG or fMRI. And then finally, we come to this non-invasive techniques like MAG. As I told you, this was the work of Ackerman in 1999, the paper that I showed to you. And so the magnetoencephalography is done by measuring the magnetic fields that are emitted by the currents that goes inside the cortex, okay? And they are detected by a very huge helmet here, yeah? But these are essentially the sensors that are there inside. So the advantage is that's non-invasive, has a very good temporal and spatial resolution. And the problem is that it's very expensive, okay? And I just a parenthesis that I'd like to do here. Both this technique here, the MAG and the fMRI, it depends on the cooling. So you have to make cool the electrodes. And what they use to make cool the emitters actually of the magnetic field, what you have to do is to use helium. So this gas, this inert gas, that is really cooled down to almost 0 degrees. Yeah, this is a very, very low temperature. And only helium can be used for doing this. And by the way, just a parenthesis, if you see somebody using helium to inflate balloons in a party, just say, no, you cannot do this because helium is a very, very rare gas that can only be mined in rocks in the earth. Okay, and once it goes to the atmosphere, it is lost forever. Okay, just a parenthesis here. Don't use balloons in party, please. Yeah, because otherwise you cannot do this kind of research in the future. And then you come to EEG, so electroencephalography. This is a classical one. You almost everybody should know what this is. So you just put the electrodes on the scalp, okay, and then you measure the electric potential on the scalp at those points, sorry. And so the advantage that says is non-invasive as the MAG, has a very good temporal resolution. It's really the cheapest technique that you can use, okay? It's safe, it's easy to use and to deploy, but has some disadvantages. So the main disadvantage is that this technique has a very, very bad spatial resolution. And it needs very sophisticated processing techniques in order to recover the sus location. So because it has a very, very bad spatial resolution, even though the temporal resolution is good, it's very difficult to say, oh, things are happening here at that part of the cortex, okay? And finally, I come to the data analysis techniques here. So you have to have very, very good people working with you to do the processing here, because you have to process this data. Sometimes they are very complicated, very, very high dimension. And then you have, for example, for MRI, you have to have this signal modeling of the hemodynamic signal. And you can study as well the connectome, so how the regions are connected to each other using the same signals. This is a very, very complicated techniques that people are developing right now. And for EEG, for example, you have to have some spectral analysis, like the continuous wavelet transform or the discrete wavelet transform. Okay, you have techniques for search detections. This is a very, very complicated mathematical techniques. And then you have to analyze the data. You have to have this model-based statistical techniques. Essentially, these are mixed effect models, but this you have to have in any study that you do anyway. And then you can use techniques of pattern recognition. So pattern recognition is the term that was used in the 60s when this technique was these algorithms were invented. And today they are called machine learning. And machine learning, actually, they changed the name because now they are using this deep learning neural networks. That is essentially the same thing that that they used in the 90s when they started doing this artificial neural networks. But now with the deep learning networks, they can have much more layers because the machines are so powerful today that you can learn this kind of networks. And then you have also to cope with the problem of high dimension, low sample size, which is called HGLSS. And there are many, many techniques, and I will let this for Adrielle on Thursday, because we invented this Rhodes technique here that she's going to show to you. And then you have to have validation procedures. These are also statistical techniques, and you have to do cross-validation in your data, bootstrapping, etc., many things. And then finally, you come to the behavioral techniques. And I think that this is a very, very sensitive point in this kind of a study, because if you notice, I talked about the acquisition techniques that are essentially neuroscientific techniques that are used to do brain imaging. So you need people that are very, very good on that, of course. And then I talked about the data analysis, this is essentially engineering stuff. So, and this is what's interesting with the people that we have here in Eicefala, because we have a mix of engineers and linguists. And this behavior technique is more related to the linguistic part of the thing here. And it's interesting because in that paper of Chang in 2010, there was a commentary in the same issue, in the News and Views part of the Nature Review of Neuroscience journal, and done by Scott and Ivan in 2010. And then essentially they are discussing several aspects that are very interesting in linguistic terms. For example, he's saying that for doing this categorization between da and ba, you can either manipulate the F2, but you can also manipulate the spectral tilt of the spectrum. So the tilt of the spectrum actually after the release, okay? And what is shown, they took this from one of the references in the paper. What they show is that you have a much more categorical perception here. This is the result of an identification task. When you have a tilt that is minus 6 dB instead of have a tilt of 6 dB. This means that you have to be very careful with what you do in your stimuli. And this is important. This is why you need this behavioral techniques to be developed here. Yeah. I just cite to you, and then I finish here some improvements that you can do. So I think that you have to have more realistic stimuli continuum, and not like the ones that the people use, because they are really people working in neuroscience, and then they just call a colleague that is doing phonetics, say, and then say, yeah, produce to me a continuum here, and I use this, okay? And I think that we really need more realistic stimuli continuum, like the straight algorithm that is quite known, and the Morphala that we develop with the people in the CEFALA, in the UFMG too, yeah. And you have to be very careful with the phonemic intervals that I use. For example, in that study that we did, I showed you to be the one, they interpolated between an A sound and a U sound. It makes no sense, because A and U in English, because the study was done with English speakers and listeners, and so you have between A and U, or it A and U. I don't know exactly how they were pronounced in the study, but you have other vowels too. You have the A, and the O vowels here. And so making a continuum like that makes no sense. Okay, if you talk about this to a phoneticist or someone who works in speech, this makes no sense. But that paper was published in Neuroimage journal. Okay, And you have also to do a better preparation of experiments with linguistically relevant guidance. For example, when you do VUT in format continua, this makes sense for me because VUT is something that's really continuous. Okay, you can really do a continuum VUT. You can even try to pronounce things in a continual way, in both in formats, like the vowels going from A to E, for example. I can pronounce this continuum. VUT is more complicated, but you can imagine these are really continuum phenomena in the speech production. Instead, for example, of place of articulation, I have a really a problem interpolating between ba and da, because they are so different in place of articulation. You cannot do something in between ba and da. Okay, and also I didn't tell here, but you can also do a very specific study by looking, for example, the attention of during the experiment. So you ask the people to recognize or to identify the stimuli or to not identify. This is passive versus active. And Adelaide will show this as well in the presentation. And then this last thing here is just for Thais, because I know that she loves that. And this is the real discussion, because we're talking about categorization all the time, but categorization is not the only thing that happens when we are processing speech. We also take care of the fine phonetic details. Even though we categorize all the time, you also say when something speaks to us and you say, oh, you are saying that in a very funny way. So you can also store this kind of information. And then the big question, I think, for the studies in the future is really to understand where the categorization and this fine phonetic details are represented in the brain. Okay, so that's all. Thank you for your attention.
So usually at this point, everybody would clap. But in these meetings, I must say thank you to Rafael for this very
sorry for taking too long.
Well, I'm sorry to make you tired for taking too long. That was a response that I saw once in Japan. But then I can tell you the story, but later. Anyway, we have time for a few questions. We should already go to João Vítor's presentation, but and this talk had a lot of different parts, and I will open time for at least one question.
You can ask later if you want, or later in the week.
Well, we should leave room for discussion about this talk later, and then move to the next presentation of João Vítor. Rafael, thank you a lot. I would have, okay. I followed this work, but I myself have a lot of questions too about.
Hani, maybe Silk, did you want to have did you have a question?
I had a comment, if I may. And
yeah,
thanks very much, Rafael, for this interesting overview. And I was wondering, one of your recommendations was that to improve perception experiments, to use morphing algorithms, right? Mm-hmm. And they've been used quite extensively by now. What I think might be a bit problematic with using them is that if you morph the two endpoints of your continuum, you morph everything that is in the signal without sometimes knowing these smaller cues that might be in there. So you might think you're focusing, for instance, just on the voice answer time, but at the same time, you're morphing the pitch of the following vowel and things like that, which might contribute very strongly as a perceptual cue to one or the other end of your continuum. And you're sort of throwing in all the cues at the same time. So I think sometimes it is useful maybe to just manipulate one of the cues that you're interested in and keep everything else stable. You see what I mean?
I fully agree, because the example that you gave is very interesting, because we're talking, for example, about pitch.
Right.
Okay? And yeah. Of course, if you do a morphing here, you have to have the same pitch of the vowel.
Right.
For the end points, of course. I agree with you. That has to be controlled. On the other side, the problem is that by manipulating, so artificial manipulating by using, for example, a CLAT synthesizer or something like that, what happens that what you produce in the middle is not really...
voltar para a gente conversar coisas boas.
Sorry? Someone was talking, I think it's Hani, that the microphone. So I was saying that, for example, if you use the CLAT synthesizer, then you cannot really control everything in the thing. And then it's better maybe to let this to the natural stimuli. But I agree with you that then you have other problems, that you have to select very, very well your endpoint stimuli. I fully agree with you on this.
Thanks.
I think we can move on now, Hani.
May I ask a question?
Yeah, go on.
Rafael, thank you for your presentation. I am not a specialist on the subject. I really enjoyed your explanation, and it is indeed a very complex subject for me. Even I've just graduated on electrical engineering. I know a bit of digital signal processing and a little bit of speech that I learned at CEFALA, and I could absorb, I think, 40% of your explanation. And I would like to ask you, I understood that this is a categorization problem, and I would like to ask you, I'm sorry if it is a silly question, but now the difficulties that you are finding in this subject, are they from the lack of data, because the methods for acquiring data are very expensive and they have several setbacks depending on the modeling you're using, or this is because the lack of a mathematical modeling that it's still being revealed, it is still being understanding by your research.
Okay, so if I understand correctly, your question is whether the problems that I'm pointing out is due to the data acquisition or to the data processing. Is this?
Yes, yes.
Yeah. Data acquisition, I think that data acquisition is okay. Today you have, I said it's very expensive, MRI, but you can do studies with this. But with EEG, you can really do very cheap studies, yeah. That's not a problem, acquisition. I think that the problem is partly in the data processing of the data. And this is what you try to do with Adriel. You try to find new ways of processing the data, yeah? To find where is the categorization, how the categorization can be expressed in terms of data analysis, yeah? But I think that the real problem is understanding, and then this is why I insisted at the end on the behavioral thing, because I think that many of the people who are doing this kind of study today, they have a very, very poor knowledge of linguistics or phonetics, essentially. And then you have to ask the right questions at the beginning, to start with, even though we can do very, very fancy data acquisition, very, very fancy data analysis right now, yeah. But I think that is something that has to be done. I don't know if I answered the question, and I don't remember how much percent did you understand from our talk?
45.
You said
45, about
45. That's very precise. Yeah. I hope you just understood the very important things.
It is a process that
it takes time to be processed.
Yes,
he will process it offline.
It's normal. That's normal.
So I think we can move to the next talk. João Vítor and Adriano, are you there?
Yes.
So thank you very much, Rafael. And João Vítor, can you share your screen with us?
Of course.
Are you allowed to share the screen?
Yes, I'm allowed. Let's see. Can you see it?
Okay, so now we have the first mini course where we try to test some techniques and tools that we believe are useful for speech scientists. The first mini course will be given by João Vítor Postamay, who's now in Germany, de Menezes, and Adriano Vilela Barbosa. I'll be there too to comment anything that you wish. But basically, the tool that we want to show is statistical learning. Statistical learning is something that is not new, but recently it has been receiving a lot of attention because it is showing itself capable of dealing and coping with a lot of problems. And as we are in speech meeting, we are going to show how statistical learning can be used for some speech problem. In this case, classification of Cantonese lexical tones. I will stop here and let João Vítor to start the talk. And João Vítor, we decided to do, Didier Desmoulins suggested that these mini courses should have a longer discussion part. So I think João Vítor will speak for something like half an hour. João Vítor, that's it?
Yeah, I'm not really sure, but it shouldn't take that long.
Okay, and then after that, we'll have time for discussion. As it's a mini course, I wonder if it's possible for people to interrupt João Vítor during the talk or not?
As far as I'm concerned, yes.
Yeah, okay, let's do the following. If it's something that it fits exactly at that point, so you are allowed to raise your hand, and then it will be able to stop. Otherwise, leave the questions for the end. Okay, so João, the audience is yours.
Thank you very much, Hani.
Thank you. Hani.
Adriano?
Yes, should I give some context about this thing? Like 1 minute?
I can give a brief introduction, and then you can give some context, Adriano. I think that would work.
Okay. That's fine then.
Okay. So thank you very much, everyone, for attending. Since Hani already did a nice introduction, I'm gonna skip to the first slide. And I'll start with a question. What characterizes a lexical tone or even a tone in speech? I would assume that most of the people here would say that it's the fundamental frequency, and whether it is the level of the fundamental frequency or the contour that the fundamental frequency has. And that is indeed the case. We have a nice figure here for the 4 lexical tones that we have in Mandarin. And they are well characterized by the fundamental frequency that they present over time. For example, we have the first tone here, which is a contour tone, which is a level tone. And the other 3 tones here, they are contour tones because they don't, they start in a determinate frequency and they end in another frequency. So the lexical tones are a very well phenomenon in linguistics. And the way that most people study them is through the acoustical signals or the fundamental frequency. But is it possible to identify those lexical tones solely based on visual information? Because speech is not only what you say and what you hear. Speech can also be what you see. So that is a problem that has been studied for a long time, with some seminal works from Sambi and Pollack and also from McGurk and MacDonald that show quite clearly that the visual aspect of speech also plays a large role in speech perception. So more specifically about the lexical tones, what we know so far about how the visual aspect of the lexical of speech presents itself in the lexical tones. Some studies shown clearly that people were able to differentiate between lexical tones with above chance accuracy solely based on visual information. So that's very important because we know now that there is some information about the lexical tones in what you see, but we still don't know pretty much what it is. And what we also know is that the lexical tone perception, mainly of the native speakers, is still mainly reliant on the acoustical information. The visual information, as stated on the other two studies, has a role, but the main drive for this perception is the acoustical information. So now that we have a problem well established, I'm gonna go on a little bit about the plan. So this is a mini course that will last 2 days. This first day, we will state briefly the question that motivates our work. I already started with that, and then maybe Adriano could talk a little while after this slide. We're gonna give a brief introduction to what statistical learning is and what does it mean and how we can apply it to our data. And today we're gonna be dealing with the acoustical part of our data set. And if there's time, I'm gonna show you some scripts that we use in the R language. So that's the hands-on classification test. The visual part of our data, and we're gonna examine how it differentiates itself from our visual, from our acoustical data. And then we're also going to perform a hands-on classification task, and then we're going to discuss the whole results afterwards. So, Adriano, if you don't mind giving a brief overview of the history of our problem.
Well, no, well, thank you, João. I just wanted to, give some context. Can you guys hear me?
I can.
Yeah,
yes,
so I just wanted to give some context about, yeah. So actually, like my first contact with this problem was like a few years ago when I was working on some data acquired by in an experiment conducted in the early 2000s at ATR Japan by Professor Dennis Burham and the late Professor Eric Bates, right? So they were basically interested in looking at visual correlates of lexical tones, right? So basically the thing is, as João has said already, we know that people are able to differentiate between lexical tones with above chance accuracy based only on visual information. So the question is, show where, another question would be, can we show where on the face or on the head the tone information is coming from or where it's located, right? So traditionally, this problem has been tackled using some sort of linear model like ANOVA, where people parameterize the F0 curves, for example, and then they try to see if there's like a difference between the means of those parameters to show, oh yeah, the first parameter is actually different across tone levels, right? But then we decided to approach this from a different perspective. And we looked at this as like a classification problem, right? So we wanted to see if visual information is able or can be used to tell tones apart, right? So basically we have some input signals. It could be like acoustic or it could be visual, right? So, and the output is just the classes, right? If you have like, for example, in Cantonese, we have 6, Cantonese 6 tones, right? Mandarin is 4, or the other way around, I never know. And we just wanted to see if using those input signals, like either acoustic or visual, we could tell those classes apart, because it's a given number of classes of tones, right? It's a discrete variable. So we were like, oh, this is a classification problem, right? So João, who did his master's under my supervision and like Maria Cantoni's co-supervision, right? He decided to look at this using these statistical learning techniques. So that's basically how this mini course came from, right? So this is kind of the history of this presentation. That's all I wanted to say. Thank you.
Okay, thank you, Adriano. And just to complete about the information that's on the slides, the data we're going to work with is the data that was collected by Professor Dennis Burnham, but a little bit later than the data that Adriano mentioned that was collected in the ATR laboratories. This data was collected in Australia, and it is a large set of audio-visual data recorded with native speakers of 3 different tone languages, so Cantonese, Mandarin, and Thai. Okay, so a little bit about statistical learning. There's a very good book that has clear and understandable information in statistical learning, and is the source. It is at the end of the presentation. And if for anyone that's more interested on the subject, I highly recommend it. So statistical learning, like Adriano said, we have predictors and we have responses that can be labels, for example. So based on a set of predictors that in our case would be the acoustical and the visual information of the tone languages, we want to be able to predict which tone is it that the people are speaking. So based on the acoustic signal that is X, I would ideally be able to predict the lexical tone that is being spoken, which is Y. And there are many models, many methods to perform this classification. And those methods work basically trying to determine some functions of X that result on the most accurate responses of Y possible. Okay, so we're gonna call these many approaches, these many statistical learning approaches, methods from now on, okay? So each statistical learning method uses a given set of data, and the set of data is composed of both X and Y. So it is a labeled set of data. So for each predictor, I have an associated response. So for each sound that I have recorded, I know exactly what tone it was spoken. So I already know the answers, and I give those answers and those data to a mathematical model that will learn how to make those associations. Like Rafael was saying in his presentation before us, it was like the pattern recognition. The methods try to recognize the patterns in X that result in the responses in Y. So an important term that I would want you to have in mind from now on is training data. So every method needs to be trained. So training data is something that we'll be using very often. So here's an example of one of the most basic learning methods that we have is the k-nearest neighbors, or short KNN. And this model is very, very intuitive, because it classifies data based on its nearest neighbors. The class with the most neighbors win, or the classificator classifies the input data in the class with the most neighbors. So for example, as I was mentioning about the training data, in this case, the training data consists of the blue and red circles. So one class is composed by the red circles, and one class is composed by the blue circles. So how was the model trained? The model was trained by putting all those data in a plane, and now I have a map. Okay, so I know which predictor or which value belongs to each class. And now I want to test my model. I want to see if this model can make good predictions. And for example, then I need test data, which in our case would be this yellow cross. And the model can classify this yellow cross based on its neighbors. I'm going to introduce here another important term, which is the term hyperparameters. Because since all the models are based on mathematical calculations, and those mathematical calculations often need some constants that change how they work. For example, if my model is a KNN with a K equal to 1, it will make its classifications solely based on the one nearest neighbor of the test data. So for example, we have the nearest neighbor here is from the class red. So this yellow cross would be classified in the class red. If I changed my hyperparameter K, or in other words, if I change how this model works, for example, with the K equals 3, I would classify this data based on the 3 nearest neighbors that it has. So I have 2 neighbors that belong to the class blue and 1 neighbor that belongs to the class red. So I would classify this data on the class blue because it has more neighbors from the class blue. So this is how one of the most simple classification methods work. There are many more methods which can be way more complex, but to give a good idea of how those methods work, we thought it would be nice to show the simple method first. So, onto our acoustical data. We're going to work here with Cantonese data, but Mandarin data and Thai data were also available to us, and we also did our processing on those data. So a Cantonese native speaker uttered 864 tokens, which may be words and syllables. Each of those words was uttered 6 times. Each time it was bearing one of the 6 Cantonese lexical tones. So each word was also repeated several times, so we could have a balanced data set based on both linguistic aspects of the syllables and words being uttered, and also on the tone aspects. So we could have the same amount of lexical tones being spoken in our data. So the F0 contour of each token was estimated with Pratt, and each token was individually checked, and some F0 estimation parameters were optimized in order to obtain a continuous curve. So for each token, we had an acoustical waveform, and we only worked later with the F0 curve that was estimated from it. Okay, now we have our acoustical data. We should be able to use our classification methods with this data. What would be our predictors? Our predictors would be the F0 curves. So this is our X, our input data, all those F0 curves. Okay, now the responses. The responses, as you may remember, are the Y. And since we are trying to classify between different lexical tones, the responses we're looking for are the different lexical tones. So for Cantonese, we have 6 lexical tones. So the responses are 1, 2, 3, 4, 5, and 6, each number representing 1 lexical tone. Okay, now about the training data and the test data. We should, before applying our method, divide our data in one part that will be used to train the model and another part that will be used only to test the model's performance. So we should split the data into 2 sets, the training data set and the test data set. Usually the training data set is larger than the test data set, but it may vary. So Some commonly used ratios are 80% training data, 20% test data, 75% training data, and so on, but it may vary. And which method are we going to apply to our data? We can apply simple methods like the KNN that I showed before. We can apply more complex methods, and that's something I will be able to show you a little bit later when I run the scripts in R. Okay, so here is one very important step that we need to do before running those statistical learning methods on our data. Statistical learning methods, they rely on linear algebra operations. So to simplify it, they put the data in matrices and they perform multiplication of those matrices. So do all the tokens have the same length? Or in other words, do all the words that were recorded have the same duration? And the answer to this question is no. We may have some words and syllables that lasted 0.4 seconds, some words or syllables that lasted 0.8, 0.6, 0.5 seconds. So our data is composed by many tokens, and each token has a different length. So when we want to order our data here, so each token is one line, one row here, we will have one row that is larger than the other, and then we won't have a matrix that we would be able to use in our classification task. And this is a problem that we needed to overcome. And our approach was based on the parameterization of the signals using polynomial fits. So since the tokens were not all equally long, we needed to find a way to make them equally long. Can you hear me? Yes, right?
Yeah, we're here.
Okay, so we performed the parameterization of the signals. And before the parameterization, the F0 contours were each described by their frequency value at each sample. So those contours were sampled at 60 Hertz. So we had one frequency value at every 1/60th of a second. So 60 frequency values per second at each second. After the parameterization, we approximated each F0 contour by a polynomial of order 3. So after that parameterization, all of our tokens were described by 4 coefficients, because as you may well or may not that well remember, a polynomial of order 3 is described by 4 coefficients. And that was the parameterization that enabled us to apply the statistical learning methods to our data. This may be a little abstract here, but after I go to the scripts, you may see some figures that will illustrate that better, okay? So let's see if I'm gonna stop sharing my screen now and start to share another screen, okay? Can you see it?
Yes.
Okay, so as many of you may know, this is the R Studio where you can program the R language. And this is a script that I wrote to exemplify the classification that we did in our data. First of all, we should load the necessary libraries and choose the polynomial order that we're going to use. So here's an important variable. So we're going to use a polynomial of order 3. Okay, I'm going to run here. It won't last that long. Okay. Okay, now I have my data, and now I'm going to apply the parameterization of the data, the polynomial fit. So we're going to use a custom function to fit a polynomial of the order, poly order, which is 3, to every token that we have. So let's run here. Okay. Let's see. Here are the theoretical Cantonese lexical tones. So the 6 tones that I've mentioned before. So we have 3 level tones, the high level, the mid level, and the mid-low level. And we have 3 contour tones, the high rising tone, the mid-low falling, and the mid-low rising tone. So we have 6 different theoretical tones that compose the Cantonese phonology. Now we're going to plot the F0 curves that were recorded by us, and we may compare them with those theoretical curves. So here are one example for each of the lexical tones of Cantonese. You have the tone 1, which should ideally be a level tone and with the highest frequency of them all. And we can see that it's actually happening. A tone 2, which should be a rising tone, which is very well characterized here by this rising part. Tone 3 is a mid-level tone, which, okay, we can see it. Tone 4 is a falling tone. Tone 5 is a rising tone. We can see the rise here in tone 5, not as steep as in tone 2, but it is present. Tone 4 is clearly falling. And tone 6 is very similar to tone 3, but with a lower frequency. So, okay, they are a little bit different from those theoretical tones, but they look like them, okay? Now let's check how our polynomial approximations work for those tones, okay? The polynomial approximations here are in red, and the actual tones are in blue. We can see that the approximations are not exact, which means that they have some error. But even with this amount of error, those approximations, they do the work for us. They maintain the main qualities of the tone, and they also make all of our tokens the same length. For example, tone 2 here is very interesting because the blue curve that we recorded has this little falling part at the end. But the polynomial fit that we did to this curve didn't have these falling parts. And that is something that is highly dependent on the order of the polynomial that we're going to use. At the beginning, I told you that the variable poly order, which was equal to 3, was very important. Because if I put this variable higher, the polynomial would have more degrees of freedom, and the polynomial would bend here, for example, to fit this blue curve better. And this may be something we want, maybe something we don't want, because if we have a polynomial with more, with a higher degree, then we would have more coefficients to describe it. And if we have more data, our algorithms will take longer to run, and they will have more trouble finding the patterns in higher dimensional data. So it is ideal to find a balance between a good approximation and a low number of coefficients. And that balance we found with a polynomial of order 3. Okay, now I'm going to create some data frames so we can perform classification. If anyone worked with R before, people use data frames for many things. And here in this chunk of code, I'm going to perform classification. Here, you can read that I can choose between 3 different classification algorithms: LDA, KNN, or a linear SVM. Today, I only talked about the KNN because we don't have that much time. And KNN is one of the simplest models. But we can also have some more complex models like the LDA and or the SVM. And we're gonna perform this classification, and then we're gonna see the results. And please don't worry right now about those 2 variables here, because they will be explained in day 2 with more time, because it is not that simple to just train a model and test it once. This is not what people do when they're publishing an article when they apply a machine learning method. They perform more robust and more complex types of validations so that the results can be more reliable. But I'm going to leave that for Thursday. Okay, first of all, I'm going to perform the classification with the first method that we saw, the KNN method. And I'm going to run here. Okay, and now I'm going to plot the accuracies that we found both with our F0 signal and also with a random signal that is used as a baseline. So here is the results. We have the accuracy here in the y-axis, and we have 2 types of data, the F0 and the random data. Okay, what can we understand from this graph? First of all, let's start with the random data, okay? What is random? It's something that doesn't have any systematic information about nothing, inclusive about the lexical tones of Cantonese. If I put some random data for our method to learn something about Cantonese lexical tones, the method won't learn anything. So the accuracy here is around 15–16%, which is quite what we expected, because since we have 6 possible classes and the data that we're inputting in our methods tells us nothing about the classes, we are just getting chance accuracy. 1/6 is 0.1667, so 16%. And this is what we get when we put random data in our classifier. So those statistical learning classifiers, they don't do magic. They are only as good as the data we use as input. So random data gives us nothing. Actually, they give us a good baseline, which is nice for a comparison. Okay, so here with the F0 data, we have a higher accuracy in the range of 75%, which means that our model was able to predict which tone was being spoken on 75% of the tokens, or 75% of the instances. So he got 3 out of 4 right, which is not as good as a human being, as a native speaker of Cantonese, for example, which would have an accuracy of almost 100%, but it is also quite good and quite better than the random data. So what we can get from this is that there is some information on the F0 contours that we use that tells us something about the lexical tones. And that means that the classifier will receive this curve as an input, will receive this curve as an input, and we'll be able to say, okay, this curve that starts here with a frequency of around 250 and goes down, there's a high chance that it will be a tone 4. Or even this curve here that stays quite stable in a high frequency, there's a high chance that it is a tone 1. Or this curve that has a very steep increase in frequency here, it should be a tone 2 most of the time. So this is how the models learn. We put the data and they see the patterns in the data so they can learn how to predict. Okay. Now I'm gonna use another classification method, which is also very simple, but a little more complex than the KNN, which is the LDA, so a linear discriminant analysis. And I'm gonna run this classification once again to see if we can achieve some better results or some worse results. I don't know, let's see. Okay, let's plot. Let's just remember, since we have around 75% accuracy for F0 and around 16% for random. So let's run it again. Okay. With the random data, we got almost the same accuracy, around 16%. But with the F0 data, we got slightly worse results, around 70%. And that shows us clearly that the methods, they have an impact on each method outputs a different results, because each method is based on a specific mathematical function, on a specific algorithm. So if we change the method, we should see most of the times not very different results, but slightly different results that can be deeply studied or analyzed. Okay, now let's check with our third method, with the linear SVM, which is a slightly more complex method than the LDA, and see what results do we get. Let's see here, still running, because since this method is a bit more complex, it takes a little while, it takes a little longer for it to run. So this is also something that you should take into account when performing those classification tasks, your computational power. I'm running this on my regular computer, and it shouldn't take very longer, but if we're working with deep neural networks, for example, depending on the size of our network and depending also on the amount of data that we use to train the network, this could take very long, very, very long. Let's wait a little longer to see what the SVM brings us. Okay, let's plot the accuracies. And now we have also accuracies around 16% for the random, but we have again an accuracy of about 75% for the F0 signal. So it's performed as well as the KNN and performed a little better than the LDA. So if I would do a very simple analysis here, I would say, okay, I got the same results with the KNN and the SVM, around 75%, but the KNN was much faster. So why should I use the SVM if the KNN brings me the same results and it is faster? So this is a very simple analysis, and the analysis that you should do in order to choose a model should not be that superficial, but it serves to tell us also that each model has its own properties. Okay, now I'm gonna show two more graphs that introduce, one of them introduces the effect of centering and scaling on F0 coefficients. in order to, for example, perform classification on the data, there are some steps of pre-processing that are usually done before it. So one of the most common pre-processing techniques that is done is the centering and scaling of the data. So this operation sets the mean of the data to 0 and its standard deviation to 1. So it should prevent that one variable have a larger impact on the classification model than the others, simply because of its higher numerical value. And it also equalizes the ranges in which the variables variate, so that all variations are considered in a more equal way. So for example, I'm gonna go back here to our data, and we should always have in mind our data. What do our data look like? What actually composes our data, so I can have that in mind when I'm choosing a model, when I'm analyzing the results, everything. Okay, the polynomial, it consists of 4 coefficients, right? And the first coefficient is the intercept, or in a more simple way, is the value with which the polynomial crosses the y-axis. So the polynomial used to fit the tone 1 has a higher intercept in general than the polynomial used to fit tone 5, tone 6, or tone 4. So this is an example of one variable that is consistently higher than the others. And we perform the centering and scaling in order to prevent that this variable has a larger impact than the others in the classification. Okay, let's see what we have here. We have our raw data here. So here is the intercept of our data in the first order coefficients of the polynomial. And each tone is represented by one color. So tone 1 is here well represented by the color red, and the other tones are here widespread. So does this image make sense? It makes sense, because at least if we perform a very simple analysis, that tone 1 is clearly different from all other tones here. And that is correct, because tone 1 it's the only tone that is more or less, it's not the only tone that is a level tone, but the other level tones have a slight dip, and tone 1 doesn't have that dip very often, and it has a higher frequency in general. So that's the intercept that I was talking about. So the variation here is the intercept. So if we have a larger frequency, it should be tone 1. And the other tones here are more mixed up. For example, tone 4 is here in purple, and it has a decreasing first order coefficient. So it is lower than 0. What does that mean? It means that tone 4 is decreasing almost always, whereas the other tones may or not be decreasing, and tone 2 is always increasing. It has a positive variation, while tone 4 has a negative variation. And this is what the approach of the polynomial coefficient parameterization brought us. We can also identify the levels and the contours of the lexical tone based on these coefficients. If we were using the frequency values, it would be way harder, because it would be very difficult to plot this data in this way, so we can see the separation of the classes. And since I was talking about centering and scaling, let's see how does the data look like after we center it and scale it. it should look this about the same. Of course, the colors here changed, but the data and the distribution of the data should look almost the same. That's because the centering and scaling, they don't have they don't change how our data behaves, how each token behaves in relation to the other tokens. It just makes it easier for our model, for our mathematical model, to deal with the data. And now I'm gonna talk a little bit about the LDA algorithm, not in detail, but I'm gonna show you how much it is different from the KNN model. Okay. Why it isn't working? Okay, I'm gonna show you here on the PDF, because I already run this data. And here's the data after the LDA does its processing.
Victor, I guess you had to change the window. You are sharing our studio.
Yeah. Share screen. Okay. That's annoying, but that's okay. Thank you for letting me know. So here is the graph that I wanted to show you. And this is what the LDA does to our data. The LDA, as I mentioned, works with matrices, with linear algebra, and it multiplies matrices along the way so it can reach a certain classification result. So given the raw data that we saw earlier, the LDA performs a rotation on the data so that the classes may be as further apart as possible from each other, and that the classes may also be as small as possible. And with that, I mean that they should be focused on one spot, in one single place, so that the difference between the classes should be the larger as possible, and the difference between the tokens of each class should be as small as possible. So here, the LDA performs some matrix processing in the data, and it makes it easier for it to classify the data. Okay, so class 1 is, you can put a line here and just say, okay, everything from this line to the left is class 1, and from this line to the right, we should think a little bit more. We could also draw a line here and say, okay, everything from this line up is class 4. Everything from this line down, okay, let's think a little bit more. Of course, we would make some mistakes. There are some tokens here of class 6, but it happens. We're not trying to have a 100% accuracy here. We're just trying to have a good accuracy. And here it is a little bit more difficult to draw some lines to perform the classification. And one of the main reasons for that is that this graph is only showing us 2 dimensions. But we have 4 dimensions in which our data is represented. And those 4 dimensions are the 4 coefficients of our polynomial. Here we only have the intercept and the first order coefficient. But you can very well imagine a 3D plot here with the second order coefficient here. And we could also represent the data in 4D and 5D, 6D, if we'd had that much coefficients. So that's a little brief introduction of what we did during my master's work with Professor Adriana, with Professor Maria, and also with Hani and many other colleagues that helped. And on Thursday, I will present how much different from the acoustic data is the visual data, and what difficulties do we have with the visual data that we didn't have with the F0 data. So for now, I think that's it.
Okay.
I'm open to questions.
We have a few minutes for questions. The thing is, the time now is open for questions. I hope João Vítor was able to explain how statistical learning techniques can be applied, for example, into tone classification. So any questions?
There are some questions in the chat.
In the chat?
From Ronaldo, I think. Yes, we can make it available, Ronaldo, for sure.
Yeah, we can.
We just need to talk to the organization so we can get emails and stuff.
Yeah, by the way, so João Vítor wanted to make the presentation available to everybody. He wanted the list of emails, and I think Leonardo Carneiro can provide it to him.
I think Maria Cantoni is with her hand raised.
Okay, go ahead. So, who? Antonio?
Maria Cantoni, almost.
Cantoni, Maria,
Hi.
Sorry.
Hi, João. Very nice to see you. I have a question. Nice to see you too. You mentioned during the presentation that speaker accuracy would be around close to 100%, right?
Yeah, but...
Yeah, how can you know that for sure? That's my question.
I don't know that for sure, but I'm pretty sure, I'm not pretty sure, but I'd say that a native speaker would perform better than 75%. But
yeah, I think
I'm just saying that
need a perception
I
test to know that, you know.
Yeah, of course, and we have some perceptual tests.
Yeah, you have that one.
Yeah, the studies from Dennis Burnham and his team, they have some perceptual tests.
Yeah, but the thing you should, well, they should remind people about is that, you know, isolated word versus like carried sentence thing, right? So the perception results are totally different, you know, because if it's in a carrier sentence, you have context, and then, you know, so you should be comparing these to like isolated word perception tests.
Yes.
Right. I don't know how much the accuracies are, but I know they are lower for the isolated word conditions in the perception tests.
Okay. Yeah. It's Rafael here. Yeah. Adrian, what do you mean by carrier phrase? Because a carrier phrase conveys no context.
I'm saying that sometimes you just give them like a word, and sometimes you give them a sentence.
Yeah, but if you use a carrier sentence, the goal is to convey no context.
Oh, when I said
so
carrier sentence, context, I didn't mean to say carrier sentence. I meant to say sentence.
Oh, I mean, in this sense. So this means that the people have other cues to recognize.
That's right.
Yeah, because I think Adrian was talking about that this data that we worked right now that I showed you, it's not the only audiovisual data that we have from lexical tone languages, from tone languages. And some older data that we also worked with presented the stimuli in two different manners. So like Adrian said, it was isolated words and words in sentences. Of course, I'm not going to reproduce it because I'm not fluent in Cantonese, but the sentence condition was like the speaker was told to say a whole sentence, and the tone that we used to work with was in the middle of the sentence in only one word. So a whole sentence was spoken, and we only went to the middle of the sentence and extracted one word and used the lexical tone of this word. Right, Adrian? Is that right?
Yeah, I just misspoke. Like, you know, the correct condition was like words in sentences, not, you know, carrying sentence. That's all Rafael is speaking on about.
Sure.
Yeah.
So this means that the data that you have were taken out of context.
Yeah, the data that
disambiguate things. Yeah.
At the data that we worked for my master and that I showed today was recorded in an isolated word context.
They were isolated.
Yes.
And do you have the perception results for this data?
No, we didn't perform any perception tests for this data in specific. We have some for some other studies.
We ourselves didn't do that, but there are like perception results.
Yeah.
Sure.
Yeah, so it will be very nice to have the results side by side so we can
exactly.
see them.
Well, the paper has been in the making for 20 years, so you know, it may be out like in the next couple of decades. I'm not kidding, and he knows that.
No, at least it's submitted now.
You even have Bateson as an author now.
Yeah.
You should hurry up before everybody dies.
No, João Vítor will be alive for a longer time. So João Vítor will be our representative.
Hopefully.
So,
just another thing, Hani. One thing that would make it difficult for us at UFMG to perform the perception task would be to find native speakers of Cantonese. Here in Germany, it could be easier, but ideally in China, it would be better.
Where is Chao Zhu? He's a native speaker of Cantonese, I think. He was here yesterday. Thais, he speaks Cantonese, right?
Yeah, I think so.
He's from close to Shanghai, so probably.
No, there's also Shanghainese. There's another variant.
You know, after the pandemics, there are many people doing experiments online.
Yeah, Maria is going to talk about
almost 1 billion Chinese run your experiment.
Mm-hmm. And this is one of is the subject of Maria Cantoni's talk this afternoon. So my suggestion, it's now 3:07. We are going to have 3 presentations today after João Vítor's talk, and I suggest we should return at 3:15. So we have 8 minutes to have a break. Is that okay for everybody? Okay, so we'll be back in 8 minutes.
Some water. All right.
Go get some water.
Okay, thank you very much.
Thank you, João. Thank you, Adriano.
Thank you, Hani.
Yeah, no, I play.
Yeah, thank you, everybody.
Yeah, thank you, everybody. So, okay, I'll turn off my microphone and camera, and we'll be back at 3:15. So, okay, now it's time to our paper talks, and we are going to start now with, let me check here.
I think that's me, isn't it?
Tuesday. Adriele, are you there? No, that is Thursday, sorry. No, it's not Adriele, it's today.
Adelaide.
Adelaide.
Yeah.
Adelaide, you are there, right?
Yes, I am.
So the first
sure.
talk in this afternoon is a labeled data set for analyzing deviant orthographic forms in texts written by children, from Adelaide Silva, Fabiano Silva, Vanderlan Aécio de Carvalho, and Lourenço Chacon. So who is going to present? Adelaide?
Me, yes. I'll try to share.
Be welcome. Thank you very much for being with us, Adelaide, and please share your screen if Leonardo Carneiro allows you.
Okay.
Everyone's allowed.
Let's try. Okay, then can you see it?
Yes.
Okay.
But make it full screen if you can.
Yeah.
You should click somewhere. Where is it?
Yes. Let me see it. I think it's here. Let's see. Yeah.
Okay, perfect now.
Okay. So good afternoon, everybody. It's really a pleasure to be here today when I'm going to present a work in progress that began with my postdoctoral stage at the computing science department at Federal University of Paraná and the Laboratory of Artificial Intelligence and Formal Methods. Fabiano Silva was my advisor. Vanderlan Carvalho is holding his master's and is helping us in the process of machine learning, and Lourenço Chacon works with us and gave us access to a database of written texts by children. And so I'm going to start with this question. Why did we choose orthography? Spelling, as you can see there, is taken as a parameter to evaluate whether an individual is literate or not here in Brazil. But, for that reason, children are submitted to an examination that evaluates their performance in spelling twice in elementary school, at the 3rd and at the 5th grade. In spite of that, 35% of Brazilian children do not achieve the minimum score to be considered literate, according to an official examination, according to the last edition of this examination held in 2016. Maybe a cause that can explain that is that there is no planning about the spelling competence expected of students in each grade, according to Moraes, for example. So considering the scenario, we started the elaboration of a system that learns the patterns of errors produced by children of elementary school. Our purpose is to help teachers in this task of teaching spelling for children. So our objectives is to use, first of all, to use computational tools as an aid to the spelling teaching process, as I told you before. We also aim to elaborate a system that identifies the most recurrent types or patterns of errors in written productions of children. We aim to elaborate also a system that simulates orthographic errors or deviant forms and relate them to the canonical written forms. First of all, we conducted an error typology. It is the first step towards the elaboration of our system, and it's based on the typology provided by Chacon and Pesarini, 218, for written productions of children in elementary school. According to the authors, there are different types of errors, like processes of omissions. So we have, for example, penny for painty. Children delete a T. Or we can have also transpositions. So we have professor, for example, for professor. Or we can have also substitutions, that is cebola with an S for cebola, with C, the canonical form. Chacon and Pesarini also claim that there is a gradients in errors that can be seen, for example, in the use of a grapheme that represents a sound in an expected position, as well as in the use of a grapheme in the expected position, but representing a different sound than the one that was expected in that context. Based on that, we used a data set that consists of the written language database assembled by the Language Studies Research Group held by Chacon. The data set contains texts produced especially for this purpose by children from the 1st to the 5th grade in a public school in the city of Marília, São Paulo. The texts in the data set result from a task of rewriting a story read by the teacher for children in each grade. All the departing texts are the same for all children in all grades. And there were 4 different productions that were collected during 1 year. So the data set was set using texts that were read for the specific purpose of data gathering for this set gathered by Chacon. And as I said, there were 4 stories, and each of them was collected in a different moment. There were 2 months of interval among the collection of the data. The data set we use is a subset of the original corpus from Chacon. So we selected 128 texts. There are 65 texts from the 3rd grade and 63 texts from the 5th grade. This gives us a total of 45,561 words, which turns out a mean of 356 words per text. We focus on texts from 3rd and 5th grades because they are the grades when children are evaluated, as I told you at the beginning of my presentation. We take for analysis the orthographic words as units. This is because the errors, as Chacon points out, apply within words and encompass syllables and segments. First of all, we proceeded a manual classification of errors following the typology of Chacon and Pesarini, and also proposing other categories of errors, because Chacon and Pesarini deal especially with errors involving consonants, and we have to think about errors involving also vowels, as well as errors involving word segmentation, that is, errors that deal or that result from prosodic categories such as the phonological word. In our analysis, Van der Laan hold a profiling using Pandas, that is an open source library specific for data analysis running on Python. And we can say that this profiling allows different grouping of error types according to the school grade. That is, it yields a grouping of errors or finding patterns that can be associated with different grades. Here we have a histogram with a distribution of types of errors in texts of the third grade. This first type of error, that is conjugated facts, put together different types of errors that can occur in the same word. For example, we can have omission and transposition at the same word. And they are the most frequent type of error in the third grade. So this is important for us to have in mind, because we are going to be back to this result in what follows. Children in the third grade also have many cases of omissions and what we call substitution, a hybrid phonological substitution. That is something like one R where they had to put two graphemes, R graphemes. But when we, I forgot to tell you that the other type refers to the type of errors involving phonological, prosodic segmentation. So things like de repente written together, for example. When turning now to data from the 5th grade, we see that omission cases are also very frequent, but the type others is very frequent, is more frequent here than for children in the 3rd grade. And as we can see, conjugated facts are now the 3rd more frequent type of errors. So we can see here a difference between the behavior of errors in the 3rd and in the 5th grade. Besides that, we can see a decrease in the frequency of combined facts in the 5th grade. They are only 13% of the total data, compared to the 3rd grade, where they represent 24% of total data. We see also that combined facts is one class of error that comprises different type of errors in the same word, as I told you before. We have also that omission type remains very close in both grades, but an examination of data reveals that omissions in the 5th grade occur mainly in the reduction of diphthongs of verbal inflected forms, or R deletion, yet the deletion of the first syllable of inflected forms of the verb to be, for example, tava for estava. On the other hand, in the 3rd grade, omissions seems to be less localized. What I mean by that is that in the 3rd grade, omissions are comprise, for example, the lack of the N grapheme for indicating the nasalization of vowels. It's something more, or even random cases in the words. In the 5th grade, the impression is that children bring to orthography facts that they have on their register, dialectal register. The other type, turning to them now, are related, as I told you before, to prosody, especially to phonological word, and it increases from the 3rd to the 5th grade. Well, what we can say, departing from that, is that apparently children start to build hypotheses about the segmentation of the speech chain more recurrently as they advance in formal education. That is not the case that children in the 3rd grade didn't have others type, but as I told you, this type of error increase at the 5th grade. That's why we have this hypothesis here. Based on that, on those findings, we can say that the profiling, confirms the hypothesis that it is possible to find patterns of errors for the different grades of elementary school. We can say also that patterns allow us to build automatic tools for accessing children's performance in the literacy process. Departing from that, we expect that our results can help teachers understand the hypothesis underlying orthographic errors, and we expect our system we expect our system to help children, we expect our system to help teacher identify the aspects to be worked on with the children. We also expect our system can help build guidelines for planning about the spelling competence expected from children in different grades of elementary school. Finally, as I told you, this is an ongoing process, and as such, our next steps consists on building automata for learning errors and associating them to the corresponding standard orthographic forms. Van der Leyen is working now on those automata. We also intend to have more data for the corpus, and then to test the system with new data. Obviously, the test of the system has to happen after the system learned the patterns of errors. So that's it. I thank you very much. And if you have any questions, I'll be pleased to answer them.
So Adelaide, thank you very much for your talk. I must admit that it was difficult for me to pay attention to the slides or to the cat behind you.
Oh, sorry, Hani.
No, it's a nice cat. No, it's really, it's a nice cat. What's his name or her name? I don't know.
Adelaide. It's a girl.
Okay.
Lalite means joy in Elfic.
Nice. So we have time for questions. Let me. So there is nothing in the chat, at least for a while. So any questions? Where is everybody? So. Thais? No?
No, I must admit, I had to nip out to get something for my mother, and I came back, I couldn't follow up. I apologize,
okay.
I'll watch it, and I had to sort something out. And by the way, Hani, at 4, I'll have to leave because it's the time I go to mom's. I'll try to stay for another 5-10 minutes, but it's the time I go there.
So, Adelaide, who did it this with you? I noticed yesterday and today that you are interested in these.
Silk has a question, Hani.
Okay, Silk, you can go ahead.
I didn't want to interrupt. No, sorry, Hani.
No, go ahead. I was going to ask about the interest of Adelaide to these techniques of machine learning yesterday and today. But go ahead to your question, please.
Yeah, I had a question about the types of errors you listed initially, right? And you had, as one of them was the substitution errors, where children then use the wrong grapheme, but it's a grapheme that is okay, actually, is maybe the more often used for the corresponding phoneme. I understand that this is also a mistake, right? But it's a mistake on a very different level, right? It's sort of not knowing for one particular lexical item the exact written form, but it seems to me very different from the others. Can you comment on that a bit?
Yeah, for sure. I was afraid we didn't have time to explore very well all the error types, so I gave you a very brief summarization of them. But the authors we follow claim that there is a gradiency that can be seen, for example, in the use of a grapheme that is possible for representing that sound in the language, although it's not expected, or it's not the standard form for that word in the language. But there is also the possibility for the children to use a grapheme that represents a similar sound in another context. For example, in Portuguese, we have the letter, the grapheme C, that can write down the sound of velar plosive in some contexts, but not before the grapheme I. And the children, some children can use it, for example, to represent the sound key. They can use the grapheme C that is not expected in that situation. So what we try to do is grouping the errors. For example, we have a standard form, and departing from the initial data, we have types or different errors that can be grouped together to the standard one, to the standard form. So our hypothesis is that there are more, there is a bigger distance between some errors in the standard form than when compared to other errors in the standard form. What we are trying to do in the machine learning process is trying to establishing these differences between the standard form and the possible errors children can make. I don't know if I properly answered your question.
Yeah, thanks very much.
Would it depend on how the distance is defined?
How the distance is, sorry?
Is defined, the definition of distance in this case, because something that could be distant in some context could be very close in another. I try to make my mind work like a mind of a child, and I'm trying to remember when I was a child and how I would think. Like C had for me the meaning of K, and that's it. Yeah. So why does it have to be C? It's key, and that's it. Ka, ki, ku, ke, ko.
Yeah, that's it. So what we are trying to do is trying to build a tool that can help teachers follow this cognitive process of children while learning the spelling of the language. So we intend this system to be an auxiliary for teachers in this task. And by measuring the distances, we can, by hypothesis, foresee what is more, what type of error is more or less expected in a specific case.
Thank you very much, Adelaide. I think we can move now to the next talk. That seems to be, I'm curious to see this next talk from Maria de Fátima Baia. And Maria de Fátima, is that you who's going to speak?
Yes, that's me.
So the title is Comparing Signing and Speech Voice of Twins, a dialogue between psycholinguists and musical studies. I became really curious about this talk, and I will let the audience, so you can start now. Okay. Thank you very much for being here. It's your second presentation, right?
Yes, it's my second one. And today, unfortunately, I'm not feeling very well. I suffer from fibromyalgia, and as I didn't sleep well last night, I'm facing the fibro fog. It's awful for the mind, but I will try. And so please forgive me if I make some mistake, because my dear colleague Waldemar Ferreira Netto, the one who did the acoustic analysis, he is not here. He's teaching right now. That's the reason why he's not here to follow me. But I think I will be able to explain. If I am not, I can give you your his email. So this talk. Okay.
Do not worry, and go ahead. And while you talk, you forget the pain.
Okay, good. Yes, I hope so. Well, this talk is very, yesterday's talk, it was very special, but this one is very special too, because my current research is on the relation between language and music in early development. And this talk I'm giving today, we are comparing the singing and the speech voice of twins. This is the outline. So I'm going to present the goal. I'm going to talk about the workshop we organized and psycholinguistics, what psycholinguistics says about early prosodic development, and what music therapy, as well music psychology says, because we are not saying the same thing. And here I'm talking like a linguist, I am, and as a music therapist as well. And then the method, ex prosodia, the application Waldemar Ferreira Netto created and he used, and the results. So the goals are, we try to establish a dialogue between the early prosodic and musical development studies, highlighting the lack of dialogue among the areas of psycholinguistics, music, and related areas. In addition to presenting this debate, we investigate through the comparison of mid-tone, I'm going to explain what it is, in singing and speech voice, if there are differences between the two modalities in the development voice of twins at age 1 to 2 years. Why we are comparing, I'm going to show you. The music literature says there is no difference at the beginning, but we in linguistics, we tend to say there is. So that's the reason why we are comparing. Before I present the literature, I'd like to talk about the workshop we organized in July, my research group at USB in Bahia, Brazil. So we had 3 amazing talks, one given by Raquel Santos from University of São Paulo. She was talking about prosody and early language acquisition. If you want to see the workshop, you can see going to the YouTube channel. It's in Portuguese. We do not have subtitles in English yet, but if you understand Portuguese, you can enjoy it. And João Pedro Reigado, he's from Nova University in Lisbon. And he came talking about the music field. It was very, very nice, his talk. And the third talk was given by Renato Tocantins from Federal University of Minas Gerais. And he came in and brought very new and very awesome considerations regarding music therapy, language and music. So please go and visit. It was very, very nice. So now talking about the literature. So when we go to psycholinguistics literature about the early prosodic development, in general, we find, perception studies saying that there is an infant's basic speech perception ability, which offers a starting point for observing how sound patterns are organized in their native language. So using the name language and thinking about language. And studies have focused on infants' sensitivities to sound properties of language. And when we talk about production, we find literature talking about universals and early international patterns as the alternation between high and low tones in intonation, short melodies, binary rhythm sequence of unstressed or stressed syllables. And well, there is a very interesting debate about if there is a relation between babbling state and first words stayed. So it's not a new debate. Actually, it's an old debate, but it's very interesting and it's very important. And we are going to say that this debate now, when we see the music literature, it's not over. So actually there's something else we need to think about, because when we are talking about language, we think about, well, is babbling important for first words? But then when you go to music literature, we hear them saying about, well, this babbling is not only for language, it's musical babbling. Actually, you are not supposed to say language babbling, but something like musical babbling. I'm going to show you. So, well, we have this debate about how important it is. In Romance language, we find many reduplicated words in early stage. And this reduplication we can explain by considering the babbling stage. So here I'm just presenting the arguments for. Jacobson was the one who was for this continuity view. But nowadays, in general, in linguistics or speech science, we talk about there's a continuity, it's important as well. So the kind of segments or prosodic aspects we find in early word states, it's related to what the child was producing before having words. All right. So, well, and there's a model, if you want to know, which explains the relation between the two states and why there is this relation between babbling and first words. I'm asking Laís, my master's student, just to explain this model.
So, word templates. Hi, can you hear me?
Yeah.
Great. Word templates, they are child-specific word patterns, and they have the effects to make many of the child words sound similar to each other, such as having a pattern of consonants and vowels that are reduplicated, for instance. They respond to challenging target forms, and they arise due to limitations and idiosyncrasies on the articulation and articulatory planning, memory, bias, and preferences of the child. So there are individual differences, and they can be selected. So they are similar to the target word, or they can be adapted in a distortion of the target word.
Yeah, I'm using this word distortion. Marilyn Wigman doesn't like it, and I forgot deleting. Thank you, Lais. So yeah, so this is a summary I tried to write for you regarding the psycholinguistics bill. And when we go to the music therapy bill, and when we go to the early musical development, what kind of information we find, actually the findings we find. So studies on perception in musical projection of babes find specific musical intervals, which are not important for language, but they are there of each stage of development. I'm going to show you some stages, and there is no distinction. So in general, they are going to assume there is no distinction between verbal or musical sounds until the first year. So we would need to be careful when we call our babbling like linguistic babbling. So it would not be linguistic. So Parazzi, she is from Federal University of Minas Gerais, from music department. She is amazing. She explains that the sounds produced by the infants to speak or to sing gradually differentiate during the second year of life. So yeah. So also from early stage, parents or baby would share what they call the pre-linguistic musical alphabet, not only linguistics, but linguistic and musical at the same time. We can find changes in timbre or melodic contours, intensity, and accent change, as I was talking yesterday when I was talking about child-directed speech. And there is a specific temporal or rhythmic patterns we can find, and also voice in a much higher register, up to 2. Here I can show you what in an octave is higher than the normal register. So I'm speaking to you using this sort of register. But if I was talking to a child, I would say, "Hi, how are you doing?" I would not be so mezzo-soprano as I sound now. So, well, they talk about spontaneous and universal, right? Later, spontaneous and universal singing stage. So, all right, there is a linguistic intonation, but there is a musical melody as well. And even until 5 years old, the literature, the music literature, they point to very specific intervals and very specific kind of singing. And here, I really like this study by Moog. Actually, the adaptation, Regado, the professor from Portugal, who participated in our workshop. So I really like this because it's very interesting and clear, and then we can compare to what we have been observing when we are talking about prosody in language development. So melodic development, we can talk about spontaneous singing and song imitation. So about spontaneous singing, what we in linguistics or speech science, we are calling just intonation. They talk about the predominance of descending intervals, short songs with repetitions of words in a specific F0 or a single rhythm. And the intervals are followed by respiratory need. And when the child is 2 to 3 years old, the songs are more extensive and organized. When they are vocalized, when they vocalize reduced intervals, the second, the third. I'm going to show you about these intervals. And song imitation as well. The child is able to repeat some fragments of the lyrics, tonal patterns, as well, rhythmic patterns. And about the rhythm, signs, there are signs of coordination with the music in this early stage. And later they can perform multiple rhythm activities of imitation and creation. Yeah, so, well, what we are going to do just to try to solve this. I'm not going to talk about the intervals. I have a PhD student, Ana Santos. Now we are trying to find these intervals. Music literature says there is this interval and it's not linguistic related, and you can find it. So it could be a cue that the child is not only paying attention to what is linguistic intonation, but paying attention to something else more general. So now we are trying to find this in another analysis, but not here. I'm not going to present here. Our hypothesis, following the debate we are trying to establish, firstly, we follow the dynamic system theory, which is the study of complex, static, self-organizing, adaptive, and open system. Why? Because this theory assumes that all systems, so language and music system as well, interact with each other in a way to come out with a more complex order than the previous one. It has been used by linguistics literature and by music therapy literature as well. So there's a very nice book by Crowley, and in this book she presents the dynamic view to approach music therapy and music as well. So our hypothesis is, well, maybe there is indeed an early unified prosodic musical system. Yeah. So what we do in order to try to understand if there is, if it's different or not, we analyze longitudinal spontaneous speech from two children, from 1 to 2 years old. They are Brazilian Portuguese speakers from Vitória da Conquista, Bahia. The corpora belongs to the GEPDEF database. It's the database I have been working on for almost 7 years. The first step was the orthographic and the IPA phonetic transcription. And the sessions we analyzed, they were monthly sessions, 30 to 45 minutes. And we analyzed singing and speech audios to compare. Here you have the explanation of what Waldemar Ferreira Netto did in the acoustic analysis. I'm not going to read it, but here you can find the details. So the automatic analysis, for the automatic analysis, we used Xprosodia. Is a computational application for automatic analysis of intonation. Waldemar Ferreira Netto, he is the one who has been working on this. It has these main functions. So the pattern detection, Brazilian Portuguese intonation modeling, and analysis of large data sets in progress right now. So the aim of our study is to compare singing and speech to speech production and the development of B and M, the children. So for this, we started from the comparison of the midtone in children's speech and sing. So this was the parameter we used in order to compare if there would be a difference of these children speaking and the same children singing. So here you have now the compositional analysis, and here you have something very nice. He put this for me, and the midtone, you can understand it as the mathematical component which emulates a speaker's tendency to keep the fundamental frequency in a central range. So what we compared is the central range, if it's different when the child is speaking and when the child is singing. So here you can see, this is the midtone, this is the final one. So here, if you want to see what is in between, we have the midtone. So here we have the emphasis and focus, superior and inferior. Yeah, and then in this application, intonation is defined as a temporal series, as you can see. Each Z is a bare intonation unit and bears fundamental frequency and as well intensity. Yeah, this one I already showed. So the results. Now we analyzed and 26 singing productions, 13 each child, and 26 speech productions, 13 each child. So we analyzed from all the sessions. Unfortunately, we didn't have time yet to compare how it changed during the development of these children, but we are going to do this. So the means we can see of speech and singing were approximated with a greater emphasis on the standard deviation. And we need to remember that this mid-tone can be understood as the mean of the F0 values obtained in a given utterance. So here the box plot shows we have the Q-square contingency statistic, as you can see here. Oh my gosh, yeah. Pointed to a significant difference only in terms of dispersion between subjects, despite a relatively low result. The other values compared still do not allow us to offer advanced conclusions, but what we can say is when these children, they are singing, they tend to be more in tune, like it's more horizontal, I would say that. So they tend to maintain the same tune, but when they are speaking, we find more variation. So yeah, here are the children that allowed me to, so I'm showing their pretty faces. So this study now proceeds as an ongoing research project. So spontaneous speech development data have already been collected and are part of the research project I am coordinating now. The hypothesis already outlined here, well, sort of a model, will be verified by conducting the spontaneous speech analysis of more babies. So there are many projects. I'm just going to show you. So here is Waldemar, my collaborations. I have Waldemar, he's a linguist. He studies prosody. Susana Correia, we have been working together for almost 10 years. She investigates European Portuguese, prosody as well, and I investigate Brazilian Portuguese. Felipe Kupski, now we are dealing with some attrition. There are twins who are bilingual and who are facing some linguistic attrition. Felipe is helping us. And Gustavo Schultz-Gattino, he's a music therapist from Aalborg University in Denmark, and he has been collaborating as well. And here's my team. So I have the music therapy team. So I'm so glad you can see the title of the PhD thesis they are working on, and there is a master student too. And I have the linguistics team as well here. And besides them, I have the pleasure to have the psychology team who these guys have been helping us a lot to deal with the therapy side. So I'm very grateful too. Thank you very much. So the reference, yeah.
So thank you very much, Maria de Fátima.
I spoke too much, right?
No, it's okay. No? We had one last, as we had one last presentation today, the last talk cannot be presented today. So we have Maria Cantoni after you. One question, are you going to be able to continue to acquire data from the children?
Yes. I'm doing this right now. We have more children, but we didn't have time to work on the data yet. More twins, more singletons.
Because I think it would be interesting to have a vertical study, I mean a longitudinal, so across years.
Yeah, that's the one. Yeah, good. Yeah.
Mm-hmm. That would be really interesting. And as you talked, I tried to remember when I was a child or the children that I've seen. And it's really interesting to measure how speech and music gradually, you would say gradually or suddenly become apart?
Gradually. I would not say suddenly, yeah. Well, actually, we need to analyze more data. And I'm now working on the intervals as well. But, well, I would say gradually, not suddenly, no. Yeah.
It's not instantaneous, I know that, no. But it's a quite fast process. It happens in a matter of a month, probably. I don't know.
Well, in music literature, they say no. They say it lasts almost 5 years to be completely, separated.
Completely, yes. But the difference from 1 to 2 years old is quite large.
Yes, yes.
Mm-hmm. So we have time for more questions, please, from the audience.
I have a question.
Rafael, please.
Yes. Yeah.
Your microphone is low.
Yeah, I cannot hear him well.
Your voice is very low. Okay, no, it's perfect.
It's good now?
No, it was and it's not.
Just a moment. So you can just look at the settings.
Your computer is somehow rebel.
I know why. It's better now, no?
Perfect.
Okay. It was a setting problem here.
Okay.
Okay, thank you for your talk. I have just a question. I think I missed the point here about the parallel between this passage from the repeated babbling, variegated babbling that you see in speech, and
Okay.
I think I didn't see this in your music examples that you gave. Yeah, does this happen as well or not?
No, I just put this because I was showing that there was a debate in linguistics area regarding if there would be a relation between babbling and first word stage. And then now we say, yeah, there is, it's very important. So what the child is producing when she or he is babbling, it's very important for the first words. And then I was just showing this part of my study to show that the debate is not really over, because when you go to the music literature, they raise another question. Actually, they claim that, well, there is no linguistic babbling either, is something like musical and linguistic at the same time. So I just put the slides in order to show that the debate is not over yet, because now we have this, what the music is claiming. I don't know if it's clear.
Yes, it's
quite
clear. Because
but I have a paper.
I thought that you said that there is a parallel between this passage between repeated babbling. No, there's no.
No, okay. Maybe, but I cannot say that because I'm doing this.
Okay, good. I misunderstood that. I thought that there was something similar in music babbling that happens in speech. Okay.
Maybe, but we are still working on this. Yeah.
Okay.
To find out.
Great.
Okay, so thank you, Maria de Fátima. I think we should follow to our last talk today, Maria Cantoni. Maria Cantoni, are you ready there? Thank you very much, Maria de Fátima.
Thank you.
So Maria Cantoni is going to, I'm a co-author of this paper because I was the supervisor of Maria Cantoni at her graduate work at electrical engineering, and a web-based open source system for speech data collection. Maria, can you share your screen?
Yes, in a minute.
So this is something, this is an answer to Atos, who spoke yesterday, because if on one hand, during the pandemic, it's hard for us to do experiments in our laboratories, it gave us a chance to develop techniques to acquire data through the internet. And Maria worked in that direction because she needs the data as well. So she's developing the tool to do that. Maria, so the audience is yours, you can start.
Okay, 1 second. And in this work, we present some developments from my completion monograph in electrical engineering course, supervised by Professor Hani, as he introduced briefly. And unfortunately, it wasn't possible to have a system, the system running up in time for the presentation, but we hope we can make it ready soon and available for everyone. And we will present some basic concepts, our plans, and what we have achieved so far. This work departs from a simple question: can we record speech remotely, ensuring high quality? Well, it's known that noise can severely impact speech audio quality. Right? And The spectrum in the left that we see here shows an example of good quality recording, and where the noise level doesn't override the speech signal. On the other hand, the image at the right shows an example of poor quality recording where the noise spectrum overrides the speech. So we have to be careful to keep audio quality to minimum quality level, to a minimum level, so we can use it. Room acoustics can also interfere with audio quality, since a highly reverberant room, in a highly reverberant room, the sound reflections are superimposed to sound waves arriving instants later, and so it can distort the signal. This question, our main question, arrived from the pandemic that completely blocked person-to-person interaction, and it led us to rethink our most basic scientific methods, and including the speech data collection processes. A solution could be, indeed, to remotely record speech, but how could we make it work, and how could we make it even better than it was before? Also, despite the pandemic, we think that collecting data at a distance has some clear advantages and with some very important ethical impacts. It can reach populations away from the research centers, people that wouldn't be able to go to a lab and participate in a data collection study. It can reach the less fortunate researchers and research teams, those with lower financial support as well. And it can promote speech assessment in natural settings, which is very important. Especially from a linguistic point of view, we tend to see this as a very important advantage. And it can also reduce research costs with displacement and infrastructure. So it has some clear advantages despite the pandemic. So we could still be using the system, a system like this, even when the pandemic is over, and I hope it's soon. But this is not without challenges. To be viable, remote data collection system would have to depend on popular technology, multimedia technology, such as computers or smartphones. But crucially, this is not the only thing. This tool, this system would have to ensure data quality and control. So the data collected with the system is useful. We have to acquire useful data. The audio should be suitable for acoustic analysis, which is highly demanding on data quality. The solution we found was to develop a system that included resources for user education and also procedure setup, and real-time evaluation of sound quality and room acoustics. With these three resources, we think we could improve audio data quality with these resources, these three types, especially. In an exploratory study we did on my completion monography, we evaluated the audio quality and room acoustics in a remote data collection setting, and we measure signal-to-noise ratio and reverberation time in 37 independent recordings. And we found then that there is a considerable variability in both these parameters. Here we have the RT, with reverberation time data, and then we have here the SNR, signal to noise ratio data. And as we can see, for both these parameters, we have some variability, and we also found that we have in general acceptable levels, and we interpret these results as indicating that remote data collection with high quality is possible, but it could be improved with the development of a specialized system, such as the one we are trying to implement now. So we plan to build a system as a web page using Shiny, and which Shiny is a code-based web design tool that uses our language. And we chose Shiny basically because for many reasons, but the main reasons is because it is flexible enough to accommodate any study requirements. We can make it whatever we want, basically, because we can change the code and the resources available. And it is open source and it's free, and it offers a safe and simple means to interact with the participants. But as it turned out, the implementation was not as simple, and we are still dealing with it. The main reason for this is that for the audio data collection, we need an audio recorder, which we didn't find in Shiny, neither implemented in our code. The same holds for the audio tests we want to perform to improve audio quality and control. So this is one of the main challenges we're facing right now. But the other resources, a form that we could use to gather text data from the participants, instructions and training presentations, and all the other materials we could use in the system. They can be easily implemented with Shiny widgets, reactive tools, or with simple R code. And then we think this is a promising development for the system. And since there is no audio recorder available in Shiny, for now, we will use an open source JavaScript recorder that we found, the web audio recorder.js. And we intend to call it in Shiny using some special functions that can adapt JavaScript to R, especially the Shiny.js package. This web audio recorder supports WAV with PCM encoding, which is uncompressed and is reliable for speech acoustic analysis. So this is our best candidate as a recorder right now, despite being implemented in JavaScript, which is a headache. But we think we can make it work soon. The audio tests we intend to implement in the system will evaluate audio quality with measuring as signal to noise ratio and some room acoustic measurements, such as reverberation time, but we are trying to find other measurements that could make more sense for small rooms too. This is another development we wish to to accomplish in the next steps of this work. The audio test results, and this is something that we think it could be really useful as a tool. That the audio tests that we intend to implement in the system, they can be used to instruct the user to adjust the recording environment before data collection. So if the test informs the user that the noise level is too high, it will prompt some tips for the user in order to reduce the noise in the environment, and also the same for room acoustics. This is what we intend to do, to use this to improve audio quality before data is collected, because we think it's better to invest some time improving data before it is collected than later trying to fix things or that fix data that is not with a good quality. And then this is it, and thank you very much for listening.
So thank you very much, Maria. I talked a lot with Maria about this talk, and especially after Atos presented yesterday, I noticed that it's really important for us to develop techniques that are user-friendly to acquire data through the internet. And we have a few advantages, like, for example, 2 years ago, people were not so used to participate in meetings like this, though we have participated, of course, but now it became something common sense, or everybody does it. And on the other hand, the software providers, they are making systems that are easier and easier to use. Anyway, we have time for questions before we finish this session today. Any questions? So a question for the audience, who among us have already tried to collect data through the internet? So only Maria, so Maria did it. Okay, in the absence of more questions,
Hani,
I think...
Adelaide Silva has a question.
Okay, there are some things here in the chat.
Yeah.
Adelaide, go ahead, please.
Okay,
she's asking.
I can read what I wrote, but Maria, first of all, thank you very much for your talk. Your work is completely necessary for us nowadays, for all the reasons you pointed out. I just want to know, Python offers tools for sound recording. Is there any special reason you did not use Python? You prefer Shiny?
This is a good question. Thank you, Adelaide. Actually, we chose Shiny because it's web designing tool already. So we can use the R language and it will be already available as a website. And so with Python, I don't know of any system. We have some, we can come and go from Python to R and vice versa, but I think if we use Shiny, it would be better to use the R language, but maybe it's not the case. Maybe we could use Python as we are using the JavaScript recorder. Maybe Python recorder could also be used, but the framework will be built in Shiny. But we can put as many widgets and resources inside it as we need and we want, and we can change that. I think this is a clear advantage of this system.
Yeah, Adelaide, we are really looking for the best possible tool to do it, and the Shiny seems to be a very nice option, but we have tried before, and different systems have different advantages and disadvantages. So, for example, we realized that we need open source. there were some systems that were not open source that we could use, but we have to be able to set up the way we need it.
Sure.
And the other thing, so Maria said more things at the end, but I think that if we can somehow instruct the subject how to get a good signal to noise ratio and low reverberation time, these two things are the main points that we have to control in order to get recordings of good quality. By the way, during this meeting here, while you speak, you and everybody, I'm trying to evaluate through my ear how the quality of your speech is. So, for example, some people have a quite long reverberation time. Some people, everybody has low noise level. And the other thing is that these tools that we have to talk here, usually they compress speech and then they uncompress speech later. So one thing that I will do is to check if this uncompressed speech loses a lot of the raw speech, raw recorded speech. So we have a lot of things to learn on how to acquire data in these virtual environments. And the work of Maria goes to a level very direct and say, okay, we have to instruct the subjects how to get high signal to noise ratio and a low reverberation time. By the way, we consider high signal to noise ratio something above 30 decibels and a low reverberation time something shorter than 200 milliseconds. That's it, Maria?
The reverberation time, that depends on the room dimensions, you know.
No, I mean, but what do we want? We would like to have a speech recorded with a low reverberation time.
Yeah, this is still to be established. And I think we have to think about the reverberation rich measurement, like something else, maybe.
Mm-hmm.
Well, Hani,
but thank you, Adelaide. And just
have more people.
Adelaide, if you have a specific recorder, could you send it to me later through email or chat? I really appreciate to have options, you know.
Okay.
And Python is open source, and if you have something in mind, I'd love to have it. Thank you.
Okay.
Rafael has
Maria,
a
send it to you.
It's a web-based application, so I guess either way you're gonna have to rely on JavaScript. So it's gonna run in your browser, so you need JavaScript.
Yeah, but every resource in JavaScript we have to put inside the system is more. It gets worse, you know, I think.
So Rafael Laboissière has a question as well.
Okay, thank you for our talk, Maria. Very nice what you're developing. And so I'm curious, this maybe is just a technical question. When you say that it's better to improve the signal before it's acquired, what do you mean exactly? What the question is, what can you modify in the remote system in order to improve this, besides just increasing the volume, say?
Yeah, what we believe is that we could invest some efforts to educate the user and to provide he or she with tools and information to improve the room acoustics and also to have less noisier situation to record the data. So the data we collect will be better than it will be if nothing was done. And this is what I meant.
I thought it was done in the computer, so this is just...
No. When you said before it's acquired means exactly. So if you acquire the data with low quality, you have to post-process it in order to try to somehow improve it. But it's much better if we can instruct the subject, for example, to move to a quieter environment, to move to an environment with more curtains or carpets in order to lower the reverberation time.
Okay, I understand. So it's instructions for
adjust the gain.
It's not really something that you can do in real time.
No, it's not. It's before. It's before.
Yeah.
Before the.
I understand. Okay.
And
good.
also to adjust the gain.
Thanks.
we don't want automatic gain control, for example.
No.
We want the gain to be adjusted by the subject and things like that.
Yeah,
Right.
it's,
I
think I have the real-time expression someplace in the presentation, and I use it to mean we are not intending to do some post hoc enhancement of the quality, you know.
Okay, no, I got it. Thank you. I was just confused.
Okay, so I think it's time to finish today. It's today we finished in time. It's 4:35 right now, and we finished on time. And we can be back tomorrow a little bit before 1 o'clock. And tomorrow we start with, let me just check. Just a moment here. So tomorrow, my computer is slow here. So what's the first talk tomorrow, Leonardo?
I mean, the first talk tomorrow
Yes.
is Silk.
Silk. So Silk starts tomorrow, so it will be a very interesting talk. And after Silk, then we have Didier with his mini course. So you should not miss it. We see you tomorrow, so please be in our room a little bit before 1 o'clock in Brazilian time. So see you tomorrow.
See you tomorrow.
Bye, everyone.
Bye.
See you. Bye-bye. Thank you.
Thank you very much. See you tomorrow.
Rafael.